Okay, in section 4.4, what we're going to be solving is optimization problems. And optimization problems are applications of our absolute min and our absolute max. So here are the guidelines for solving application or optimization problems. And at first it may just be a lot of words to you, so once we look at an example, this will probably make more sense. First of all, you always want to read your problem and assign your variables. If applicable, draw a picture. We're going to identify what we call objective function. So that's the function that that's going to be optimized. So it's a function where we need to find a minimum or a maximum. We're going to identify constraints, and constraints are just limits on our variables that we're going to use to write our objective function in terms of one independent variable. Once we have our function written in terms of one variable, then we're going to find our interval of interest for our variable. And then we'll use calculus to determine if we have an absolute min or max. So again, that's just a lot of words. So let's look at example 1 and see what all this means. Well, first of all, in example 1, we're supposed to find two positive real numbers whose product is 40. And these two positive real numbers need to have the smallest possible sum. So since we're supposed to be finding two positive real numbers, that's going to be our variables. So I'm just going to use x and y. So I'm going to let x and y be my two positive real numbers. Okay. So since x and y are my two positive real numbers, the next thing I want to do is identify my objective function. Since these two numbers are going to have the smallest possible sum, smallest means we're looking for a minimum sum. And that would be my objective function. I'm going to add these two numbers up and get a smallest sum. So I'm going to let S stand for sum. So I can write S equal to the sum of x plus y. Right, so this is my objective function. This is what I want to minimize. So now I want to take that objective function and I want to write it in terms of one variable, either x or y. And that's where the constraint comes in. The constraint is that the product of these two numbers has to be 40. So I know that x times y has to be equal to 40. Again, that's my constraint. That's what I'm going to use to write my objective function in terms of one variable. It doesn't matter which one I choose to substitute. I'll just go ahead and solve my constraint for x to write x is equal to 40 over y. My sum equation is now s equal to 40 over y plus y. Now that I have my objective function written in terms of one variable, I need to identify the interval of interest. So that's just all the y values that we can use. So since y is supposed to be a positive real number, my y values have to be in the interval from 0 to infinity. Okay, so again, this is the interval of interest. Okay, so how we figure out what a minimum or a maximum is, and here we're talking about absolute minimums and maximums because this is supposed to be the smallest possible sum, so it's an absolute min, is we use calculus. Remember, to find mins and max, we look at the first derivative. So I'm going to take the first derivative of this function s And it's probably easiest if you look at s, and in fact, let me rewrite s, equal to 40 times y to the negative 1 plus y. That's going to be easier for me to take a derivative. So s prime is going to be negative 40 y to the negative 2 plus 1. Or s prime equal to negative 40 over y squared plus 1. Now I have to find my critical points for my first derivative. In this case, if I can see that if y is 0, my derivative will be undefined, except for 0 is not in my interval of interest. So I'm going to ignore that and see if I can get another critical point by setting this derivative equal to 0 and solving for y. So if I subtract 1 multiplied by y squared, let's see, I get y squared equal to positive 40. So y is equal to plus or minus the square root of 40. Now again, y has to be a positive real number, so I can throw away that negative value and look at my critical point for my derivative as just being the square root of 40, which I'm going to write as 2 square root of 10. Okay, I have one critical point. I'm going to go back to this interval of interest. So I have one critical point that's 2 square root of 10. I need to test to see if 2 square root of 10 gives me an absolute min or max. So I'm going to take my first derivative, and I'm going to plug in maybe 1 into my first derivative, and that would give me a negative. If I plug in something larger than 2 square root of 10, like 10, that would give me a positive in my derivative. So it goes from negative to positive. This is a local min, and then by theorem 4.5, I believe, theorem 4.5 says if you have one local min, it's an absolute min. So we've just shown that critical value 2 square root of 10 gives us an absolute min. So when y is 2 square root of 10, we have one of our positive real numbers. Now if you plug in 2 square root of 10 into your constraint and solve for x, you'll also get that x is the same, 2 square root of 10. So we can conclude that our positive real numbers are both 2 square root of 10. That's the process of optimization. Define variables, figure out what you're supposed to maximize or minimize, and remember that these are absolute max, absolute mins, they're not local max and mins. Find your constraint, your interval of interest, and then take the first derivative so you can locate critical points. Test that first derivative to see if you have an absolute min or max. Okay, let's do another example. In example 2, this is a geometry problem, so I'm going to get to draw a picture on this one. In this problem, you could use geometry without calculus to probably figure out what the largest area would be, but we are in calculus, so we're going to use calculus. So fencing is needed for a rectangular plot of land bordering a riverbank. So here I have this rectangular plot of land and it borders a riverbank. Fencing is only needed for 3 sides. We don't need fencing on the side that is on the riverbank. So I'm going to have some length and some width. I don't need a let statement because L and W are generic length and width. We always use that. I know that fencing is only needed for 3 sides, and I have 104 feet of fencing. So I could see that if I take L plus 2W, that has to be 104. This is my constraint. I'm supposed to find the largest area that can be enclosed. Largest area means max area. So this is our objective function. It's the area function of a rectangle. So the area is equal to length times width. Next step, take that objective function and write it in terms of one variable. So I'm going to take my constraint and I'm going to solve it for L by subtracting 2W from both sides. So the area is 104 minus 2W times W. Next, I need to find my interval of interest. Well, the area can't be negative. And look, it's already factored on the right-hand side. So if we look at W, it's either going to be 0 or 52. So W has to be in the interval from 0 to 52. But notice I can also write the interval as a closed interval with brackets. In our first example, I couldn't use a closed interval because it was any positive real number, so I had to go to infinity. But here, I can use either an open or a closed interval. So the difference is that if you're using an open interval, as we did in the first example, you're going to be using theorem 4.5 to verify if you have an absolute min or max. If you have a closed interval, you're going to be using our very first theorem, theorem 4.1 from section 4.1, that said if on any closed interval, you're guaranteed to have one absolute min and one absolute max. So I'll use both of them to verify min or max. But our next step is to go ahead and take the derivative. I'm going to go ahead and multiply through by the W to write 104W minus 2W squared. So the derivative would be 104 minus 4W. If I set that equal to 0 to find my critical points, I have W is equal to 26. Oops, sorry. Okay, so I know that's a critical point. I don't know if it gives me a maximum area. I have to use calculus for that. So let's go ahead and look at the open interval. So this is going to go from 0 to 52, and my critical point is 26. When I test my derivative for the area, let's see, if I put in 1, I get a positive, and if I put in 30, it's going to be negative. So we went from positive to negative. That gives me a local max, but since there's just one local max by theorem 4.5, that local max is an absolute max. Now, if I have a closed interval with brackets, I'm going to use theorem 4.1. So theorem 4.1 means you don't have to look at the sign, whether it's positive or negative. Remember, all you have to do is test the endpoints and the critical point. The largest value would be your absolute max, the smallest value would be your absolute min. So if I put in 0 for w, my area function is going to be 0. If I put in 52, my area function's 0. If I put in 26, the area function is 1, 3, 5, 2. And since that's the largest value, that will be my absolute max. In this particular problem, we're not supposed to find the width and the length that gives us the largest area. We're actually supposed to find the largest area. Well, using that closed interval, I've already found the largest area. It's 1, 3, 5, 2. So the largest area is 1,352 square feet. Our last example is a little bit different from the other two. We're given all the variables. All we have to do is figure out what our objective function is, what our constraints are, and so on. So we're supposed to find some point on the line y equal to 2x that's closest to the point 30, 0. I'm going to go ahead and draw a diagram. And this is not going to be to scale. So let's say this is 30. Now the only thing I know is that my point lies on the line y equal to 2x. So that would be a kind of a steep line. So this point I'm looking for, P, is going to be on this line, so it's probably going to be above the x-axis. Again, it's not to scale. I just want to get an idea of what I'm looking at. Okay, so we're supposed to find the point closest to 30, 0. So what we're looking at is the closest or the smallest distance from our point to the point 30, 0. Now I'm going to have to figure out how to write my point. So any point on the line y equal to 2x is going to have, for every x value, the y value is just 2x. So that's what my point P is going to look like. I'm going to be minimizing, right, because it's closest. It's going to be a minimum. Minimizing the distance between these 2 points. So the distance formula, if you recall, subtract the x's, square them, plus subtract the y's and square them. X minus 30 squared minus 2x minus 0 squared. So if I get rid of the parentheses, multiply everything out, combine like terms, I'm going to get to 5x squared minus 60x plus 900. So skipped a few steps there. All right, I don't want to, this is my objective function, and I really don't want to take the derivative here because of the square root. So logically, if I square both sides and look at just 5x squared minus 60x plus 90, if I find the critical points for that function, they should be the same as if the square root was there. But I don't want to take the derivative of d squared, so I am going to substitute maybe a capital D. And I'm going to call this function capital D. So this is going to be my objective function that I want to minimize. Before I take the derivative though, I have to think about the constraints that I have on my x values. Unfortunately, there are none. My x values are any point on the line y equal to 2x. The domain of that line is all real numbers. So I'm going from negative to positive infinity. So we've looked at intervals that are closed intervals, open intervals where we have some nice endpoints like a 0 and a 52. Now we're looking at, there's no restrictions on my variable at all. So hopefully I'll just get one critical point when I take the derivative of my objective function. And that derivative is going to be 10x minus 60. So if I set this equal to 0 to find my critical points, I have that x is equal to 6. So I have no choice here. I'm going to have to use theorem 4.5. So when I look at the derivative, and maybe look at putting in 0 into my derivative, I get a negative. Maybe something larger like 10, I get a positive. So the derivative goes from negative to positive. This is going to be an absolute minimum, which is exactly what I want because I'm minimizing a distance. So the question was, what is this point? So the point is well, the x value is 6, so the y value must be 12. Part B was, what is the minimum distance? So we just have to plug that back into the distance formula to get 30 minus 6 squared plus 12 squared. Since x is 6. Let's see, after doing a bunch of work, I get the square root of 720, which is 12 square root of 5, I believe. So that would be the minimum distance. It would be 12 square root of 5, and I don't have any units, so I'm just going to put the distances. Square root of 5. If you want to put the word units at the end, that's fine too. Alright, so that's it for 4.4.